Okay, so we are starting our slideshow here. I'm going to take a moment to allow the volume adjustment to be set, and while we're doing that, everyone should have gotten out that handout from Monday so that you are looking at the sheet that says class questions for lesson 7.5, and we worked through the first question on Monday, and we're now going to be having a look at the other two questions. So it's equilibrium calculations part 2. So the first instruction is to read question 2 from that previous day's handout. So if at 1,000 degrees the initial concentration of water vapor is 0.100 moles per liter, what will be the concentration of hydrogen gas at equilibrium for the decomposition of water if the equilibrium constant is 7.30 times 10 to the negative 18 at that 1,000 degrees? Temperature has to be consistent with the reaction equilibrium constant. So if those two values aren't the same temperature, you can't use the equilibrium constant because we know that temperature affects the constant value. So how do we start this thing? Well, we are going to make a couple of general assumptions here. Let's get these down first. So first of all, if K is small, and remember we think about K as products over reactants. So if K is small, start with only reactants. Oppositely, if K is large, start with only products. In English, what does that mean? It means that we've only got a very, very small amount of reactants, and since Kc has an exponent of 10 to the negative 18, we don't expect many products. So we can safely assume that our starting concentrations are 0 and we just have a whole bunch of the reactant. So now we're going to need a reaction, and we know that it's for the decomposition of water. So remember, leave a couple centimeters on the left-hand side of your page. We're going to start the reaction here with H2O gas in equilibrium with H2 gas plus O2 gas. So far, so good. I'm going to just switch colors for a second to balance this thing. So we're going to have 1, 2, and 2. All right, so we've got this thing nicely balanced. We now know we're going to have to go to an ice chart. So on the left-hand side, I in moles per liter. Let's make sure we get our units in here. C in moles per liter and E in moles per liter. I know I can jump straight into moles per liter because the question starts off with an initial concentration of water vapor. Doesn't give me moles like we did in question 1, so we can go straight in and fill in that the initial concentration of water is 0.100 moles per liter. I'm recording it to the correct number of significant figures so I can look back to it later. The initial concentration of hydrogen, there's none, and there's no oxygen. This works out real nice because now we know which way the shift is. It has to be to the right, and so we're going to give up some water, we're going to make some hydrogen, we're going to make some oxygen. We bring down those coefficients. Nope, sorry, I have to change color there. And as I keep saying, let's make our math teachers happy by using x as our variable. Okay, so now we can write the equilibrium by just looking at those previous two lines. So it's going to be 0.1 minus 2x, positive 2x, and positive, there's a mistake. We're going to have to cross out that. And it's just 1x. My mistake. So it's just 1x. I'm sure if you guys had been here when I was writing this, somebody would have raised their hand and would have pointed it out for me, but I don't have that luxury right now. So you're going to leave a couple lines underneath because the question says we just need the concentration of the hydrogen gas. So this is what we're really looking for right here. And so we're going to have 2 times whatever the concentration works out to be. We'll deal with that in a few minutes. So I'm going to need to go up or go to the next page in order to have this. So hopefully everyone's got this done. So I'm going to advance to the next slide, and that just gives me more space to write. All right, so now we've got to figure out that equilibrium expression. You guys can still see on your page that K has to equal the concentration of products over reactants. So that's going to be the concentration of the hydrogen gas at equilibrium squared times the concentration of the oxygen gas at equilibrium first order divided by the concentration of H2O gas at equilibrium squared. So there's our expression. I have to write the expression first before we go any further. Now we're going to substitute. The value of K is 7.30 times 10 to the negative 18. That's that really, really tiny number. And that equals, and now we go to our equilibrium expression, and we have the concentration of hydrogen gas is just 2x. That's in brackets because we have to put the squared. That squared comes from up top here. And then we have to put the concentration of O2, which is just X, and it's first order. We divide by the concentration of the water vapor, which is going to be 0.1 minus 2x. And that quantity is squared as well. So we look at this expression and we're going to ask yourself the question, so what's the process? How do we deal with this thing? And last class we looked at the idea of the perfect square, and we look at the numerator, and the numerator is not going to simplify to a perfect square. We know that because as we simplify the numerator in this, we're going to get the left side still equal to 7.30 times 10 to the negative 18. The numerator, which is what's going to change here, that 2x quantity squared is now going to equal 4x squared times x all over 0.1 minus 2x quantity squared. All right, so the numerator is now going to simplify to 4x cubed. And the rest of our expression stays exactly the same. The denominator is 0.1 times, or sorry, 0.1 minus 2x squared. And the left-hand side is still 7.30 times 10 to the negative 18. All right, so the numerator is clearly not a perfect square. The denominator happened to be a perfect square, and the left-hand side, the value of k, is some really, really tiny number. And this is the point in time where the pure mathematicians really don't like me, because what I'm going to do is I'm going to make an assumption. Assume. What am I going to assume? Well, I'm going to look over here at this expression, and I'm going to say, well, because the value of k is really small, we're not going to use up a lot of water. The value of x is going to be really tiny. And so I'm going to look inside that bracket, and I'm going to copy down the parts of the 0.1, leave a little gap, and then the 2x. And I'm going to make an assumption that the value of 0.1 is much greater, that's why there's two sets of arrows, or the wedges there, is much greater than 2x. Why can I make that? Well, because the value k is really small, and so I'm not going to get many products. If I make that assumption, therefore 0.1 minus 2x approximately equals, and some of you have seen the two wavy lines used for that. Sometimes I'm going to put it up here. Sometimes you've seen two straight lines with a dot over top. Not sure which system your math teachers are going to use. I'm probably going to use the top one. the 0.1 minus 2x approximately equals 0.1. Okay? And we'll check that out later. But we're going to make that assumption. And when we make that assumption, this term in my denominator disappears. And some of you are going, wait a minute, how can I just take out that part? Well, because I assumed it's really small. So small that it won't matter. Now let's see what happens to my expression when I make that assumption. The left-hand side does not change. It's 7.30 times 10 to the negative 18. The right-hand side still keeps that 4x cubed in the numerator. The denominator, however, is now going to be 0.1, close the bracket, squared. I can make that statement because I've assumed that the negative 2x is so small that it's negligible compared to that 0.1. Well, suddenly this went from a cubic function that was going to be very hard to solve to a cubic function that's a lot friendlier to solve. So now I'm going to multiply both sides by the denominator. And so that means I'm going to get 7.30 times 10 to the negative 18 times the denominator, which is 0.1 close bracket squared, and that simply equals 4x cubed. Okay, so I'm going to give you a moment to make sure you've got that all copied down before I move on to the next slide. Moving on to the next slide in 3, 2, 1. All right, so now I've got an expression that was 7.30 times 10 to the negative, and when I multiply that 0.1 squared, I get 0.01, and multiply the exponent in now, I've got negative 20. That's what the left-hand side now equals. That's going to equal 4x cubed. Okay, so if that equals 4x cubed, I now need to divide both sides by 4. And now my right-hand side is going to simplify to x cubed. And the right-hand side is going to be 7.30 divided by, or 7.30 times 10 to the negative 20 divided by 4, which when you work that out on your calculator, so take a moment, put this number into your calculator, 7.3 times 10 to the negative 20, make sure you're using that EXP button, you should get 1.825 times 10 to the negative 20. Okay, so now we've got x cubed equals that really, really tiny number. And so now I'm going to take the cubed root. Now on some of your calculators, you're actually going to see a cubed root button with a little x in there. And so that's going to make it really easy if you have that. If you don't have that, you're looking for a button that has an x to the root y or something like that. If you're having trouble finding it, show the calculator to the person sitting beside you and hopefully they can help you find it. If not, ask the supply teacher if the supply teacher can help you find it, and if not, in desperation, hang on till Thursday and I'll show you where it is, if your calculator's got one. So we're going to take the cubed root of both sides. Oh, and I've been very, very slacking because I forgot my little dot over top of my equal sign for approximately equal to. I probably forgot that on the last slide. Okay, so when we take the cubed root of a cubed number, the right-hand side is going to simplify to just x. So now we need to take the cubed root of 1.825 times 10 to the negative 20, which is why I had you do the calculation earlier. Take the cubed root, and you're going to get approximately 2.63 times 10 to the negative 7. All right. Now, that's the value of x. But we made an assumption, and so we need to check the assumption. Because we made an assumption, but if the assumption isn't good, then we can't use it. So your textbook talks about the rule of 20, which is one way of doing it. And so if you're able to read the textbook and like that way of putting it, go ahead and use it. I'm going to show you a different style. Both of these are valid. So what I use is called the 5% rule. The 5% rule says that the small number must be less than 5% of the large number. That's what it means. Okay, so my original number was 0.1. That was the original concentration, because the assumption was that we had, and I'm going to go back, if it will let me. Oh, crap, it's not letting me. That could be bad. Oh well. So the assumption was that we were able to have 0.1 is much greater than 2x. That was our original assumption. 5% of 0.1 equals 0.005. Now, 2x equals 2 times 2.63 times 10 to the negative 7, which is 5.26 times 10 to the negative 7. 0.005 is in fact bigger than 5.26 times 10 to the negative 7. Therefore, the assumption works. That means that this value of x can be used in our calculation. So the concentration of hydrogen that we're solving for you guys are able to go back up to your chart. For some reason I'm having trouble getting this to let me go back to my chart. No problem. The equation for that was 2x. Well, I fortunately, right over here, have 2x. So that means 2 times 2.63 times 10 to the negative 7, which equals 5.26 times 10 to the negative 7 moles per liter. And since the question only asked me to work out the concentration of the hydrogen gas, that's it. That's done. We've got everything done. We've checked it. We don't need to work out the concentration of the oxygen or the concentration of the water. But if you wanted to, the assumption says that the concentration of water really didn't change. So far, so good? Excellent. I know that's a rhetorical question. So we're going to move on to question number 3. So read question 3 from yesterday's worksheet, and then we're going to deal with our reaction. So the formation reaction, okay, now that was probably the wrong word because I want this as a synthesis. I don't want 1 mole of product. So that was a mistake on my part. The formation reaction of hydrogen iodide under a specified temperature has an equilibrium constant of 64.0. If at that same temperature, a 5-liter flask is filled with 2 moles of hydrogen gas and 4 moles of iodine gas, what will be the equilibrium concentration for all these substances? All right, so again, we need a reaction. So it's the formation reaction, which was a typo on my part. So we're going to start out with H2 gas plus I2 gas in equilibrium with HI gas. And being good at chemistry, we're going to balance this and say that we're going to use 2 products and 1 of each of those reactants. So we got this thing nicely balanced. Next, we know we're going to need an ice chart, but because the question gave us amounts in moles, not moles per liter, we're going to start out with I in moles and get our starting information down from there. So we've got 2.0 moles of hydrogen. We have 4.0 moles of iodine, and we do not have any hydrogen iodide, so that's 0. We've recorded each of our initial amounts into the correct significant figures, so we know that our final answer has to be the 2. This time we're going to now add the I in moles per liter, and we can make a little note someplace that the volume from the question was 5.00 liters, and so we know we're dividing each of these numbers by 5. So 2 divided by 5 gives me 0.4, and 4 divided by 5 gives me 0.8, and the concentration of hydrogen iodide is still 0. So far, so good. Change in moles per liter and equilibrium in moles per liter. So we know it's going to shift to the right because we have no products. So it's going to be negative 1x, negative 1x, and positive 2x. And that means my equilibrium concentration for the hydrogen is going to be 0.4 minus x. Iodine is going to be 0.8 minus x. And then the hydrogen iodide will be positive 2x. Okay. So the question says, what will be the equilibrium concentrations of all substances? So we're going to end up solving for all 3 of these. Okay, that will be something we can get to later. Now we don't have to figure out which way this thing shifts, so we can jump straight into our equilibrium expression. I'm going to move on to the next slide in 3, 2, 1, go. All right, so the K value equals concentration of HI gas at equilibrium squared divided by the concentration of H2 gas at equilibrium first order and concentration of iodine gas at equilibrium, again first order. All right, so the K value is 64.0. Substituting from our equilibrium expression, the numerator is going to be 2x quantity squared. The denominator is going to be 0.4 minus x and 0.8 minus x. Both of those first order. And so I look at this and I'm going to say, it's not that perfect square. The value of K, while kind of bigger than like 10, is not really large, so I can't assume that it's all one or the other, which means I'm going to be solving a quadratic. So at this point in time, everything that I do is going to be focused on getting this into that standard form of ax squared plus bx plus c equals 0. So this is going to take a little time. The numbers are not pretty. Oh well, that's how it plays out. So we can do this in a number of different orders. Some people like to get rid of the denominator first. Some of you will want to use FOIL first. I'm going to start by the denominator. So I'm going to get rid of my denominator by multiplication. And so I'm going to multiply the entire expression by both pieces of that denominator. So I'm going to get 64 bracket 0.4 minus x and 0.8 minus x equals, and I'm going to expand at the same, now I'll do that in another step, equals 2x quantity squared. This time I'm going to use FOIL on the left and expand. So I'm going to take care of expanding on the right. I'm going to use FOIL on the left. For those of you who have forgotten or weren't taught what FOIL stands for first, outside, inside, and last in that expression. Because I'm going to deal with the 64 after because it'll be easier and less work. So I'm going to have 64. I'm going to use a nice big square bracket. 0.4 times 0.8 is 0.32. Outside is 0.4 times negative x, which is negative 0.4x. Inside is the 0.8 times negative x, which is negative 0.8x. And then negative x times negative x is positive x squared. Close the bracket. That equals 2x quantity squared, so 2 squared is 4, and x squared is going to be x squared. So that gets my FOIL and my expansion. Now I'm going to collect like terms on the left-hand side because I've got two values that are just x terms, and I want to collect those before I do my distribution. So we're now going to get 64. I'm still going to use that big square bracket. 0.32 minus 1.2x plus x squared. Close my bracket, equals 4x squared. Now I'm going to distribute the 64. So this is only a change on the left-hand side. So now it gets to be a little more complicated. I have to do some math in my head, or I can break down and use a calculator if I'm desperate. So 64 times 0.32 is 20.48. I now go to expand this over. So I've done this first one. Now I'm going to do this one. Then the last one, I'm going to go all the way over here and do that one. So next one is 64 times negative 1.2. That's going to be negative 76.8x. The last one's easy. It's going to be positive 64x. And that all equals 4x squared. So from this point on, what I'm going to do is I'm going to get my order, because remember I wanted ax squared plus bx plus c, and I'm going to subtract the 4x squared, because I want all those terms on the left-hand side so I get 0 on the right. So I've got 64x, almost missed that x squared here. Good, got that. Good, that makes more sense. So now I'm going to take my 64 on the left and my 4 on the right. I'm going to subtract the 64x squared minus the 4x squared. And so now I'm going to get, in order, 60x squared. Sorry about that. I assumed you didn't want to hear the rest of the announcements. Okay, now we're going to just get this in the correct order. So it's negative 76x plus 20.48 equals 0. So now we've got this in ax squared plus bx plus c form. So let's make sure that we know that that's a, that with the negative sign is b, and that whole creature is c. All right, so at this point in time, you have to solve the quadratic. Now, I asked the question earlier if some of you have a tool like a calculator that will solve a quadratic formula, And if you happen to have it, great, go ahead and put your values in. If not, you're going to have to remember that the quadratic formula is written something like this. X equals negative b plus or minus the square root of b squared minus 4ac, that's all underneath that radical sign, divided by 2a. And you're going to have to substitute and solve, and it's going to take you a while. So for those of you who don't have a calculator that'll solve this thing for you, you're going to substitute all that in, and it's going to take you a few minutes. Tick, 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 tick. Okay, time's up. Now, for those of you who can put it all into your calculator, I'm going to move on to the last slide. And you're going to get two values. X when you finish the calculation, and if the slide teacher wishes to, he or she can elect to pause the video at this time if you want to give people enough time to actually work out these values. That might be a good idea, just because we want to see if people can get the numbers. So once most of us have the numbers, you're going to get two values. One of the values is going to be 0.9012, and the other value is x equal to 0.3787. So again, if you wish to, this might be a time to pause in case there are people who are going, how did I get that? I don't get those numbers, and we can fix these things. And once we've got that worked out, you will discover that of the two values, now we got a bit of a problem because, well, one of them can't be right. And the question is, well, how do we know one of them can't be right? It's surprisingly simple. Concentration can never, let's underline the word never, be negative. So, I know what a positive concentration is. I know what having no concentration is, but I have no clue what it means to have less than nothing in my solution. So you can't have negative concentrations, which means I've got to go back to that equilibrium line. So since I'm having trouble going back in my slideshow, I'm simply going to recopy equilibrium in moles per liter here in order, because the H2 and then I2 and then the 2HI had expressions of 0.4 minus x and 0.8 minus x and positive 2x. Now when I look at these, if I take that first value of x and try and put it into either expression for H2 or I2, I will quickly realize that I will get a negative value for concentration, and so this one can't be used. Generally speaking, it's the large one that you can't use. So, therefore, the value is going to be 0.4 minus 0.3787. And because I look back at my original sheet and I can only have two significant figures, when I do my subtraction, I'm going to get 0.40 minus 0.3787, that's going to round to 0.38, and it's going to be 0.02 moles per liter for the hydrogen. The iodine is going to equal 0.8 minus 0.3787. That's going to equal 0.42. And for the concentration of hydrogen iodide, that's going to be 2 times 0.3787. And so this time we get 0.76 moles per liter. So that gives us all of our concentrations for all of our respective substances, and we can only have two significant figures. This time around, because of the subtraction, the first one, it looks like there's only one, but that's done to the correct number of significant figures. So that gives us all of our processes. So In summary, we have perfect square, we have assumption, and we have the quadratic formula. And each of these has a specific situation. Generally speaking, the assumption will be used whenever you run into a cubic or that value of k is really small or really large. Perfect square is kind of that unusual thing to avoid having to use a quadratic formula because it's faster than using the quadratic, but just be expecting that you're going to have to use a quadratic formula. I hope you found this informative. If you need to go back and review it, I had said that I'm going to share this thing with you guys through OneDrive, and so I intend to take care of that so that you all have it. All right, I hope this was informative, and you have the rest of the period to work away at your homework either from Monday when I taught the first half of this lesson or today's homework, which is the second half of this lesson. If you're comfortable with it and you want to talk about some of those results, because I know some people didn't get one of those labs from yesterday's done, feel free to use a few minutes to share the data from that. And if it leads to any conversation about why did we get certain shifts for Le Chatelier's principle, that would be okay too, because I know you guys will stay on task. Thanks very much, and any of your questions we will take care of tomorrow. Have a good afternoon.